Physical Science. This is Mr. B, and we're going to jump right into our next part of Section 2. Again, this video is going to focus on some more examples of how energy is converted, and we talked about friction playing a role. We're going to talk about some other examples of energy conversions, and actually how we can calculate energy conversions as well. So to jump right in, one example that they're going to have here is they want to know what energy conversions take place as objects fall towards Earth. So this is going to be kind of a big overriding theme here, that gravitational potential energy of an object is converted to the kinetic energy of motion as the object falls. So this is one of our most common energy conversions, and that's what our next slide is going to kind of lead off with, is that potential being converted into kinetic. And we're going to take a look at some kind of real-life examples of how that can actually happen. Again, like I said, one of the most common is between potential energy and kinetic energy. Again, an avalanche brings tons of snow from the top of a mountain to a valley floor. Again, so that's, it's all stored as potential at the top, and then as soon as it starts moving, it's converted into kinetic. And then the elastic potential energy of a compressed spring is converted into kinetic energy as the spring expands. Again, I think the example from earlier on was like the shock absorber on a bike. Again, that gets compressed, it has a bunch of potential energy, then as soon as released, that's all converted into kinetic energy. And then energy conversions can go from kinetic to potential or from potential to kinetic. They can kind of work both ways here. And we're going to go over, again, some real-life examples here really quickly, and then we'll actually get into some problems here of how you can calculate the energy conversions. So some gulls, like a seagull, use energy conversion to obtain food by dropping oysters onto rocks. Again, right there at the top when it's flying with the oyster, has a very big gravitational potential energy. As soon as it drops it, it's converted into kinetic energy, and the kinetic energy will cause the shell to break on collision with the rock. So that's one example. Again, real life. Again, birds can figure out how to use energy conversion, then I'm sure we can too. Another one is a pendulum. And we might try to find a cool example to do with this in class a little bit later on. But a pendulum consists of a weight swinging back and forth from a rope or a string. And we'll see an example of one, but I'm sure you guys have all seen a pendulum at some point in your life. And at the highest point in its swing, the pendulum has zero kinetic energy and maximum potential energy. So again, when it's swinging all the way over to the left as far as it can go, it has maximum potential and no kinetic. And then as the pendulum swings downward, the potential energy then is converted to kinetic. And when it's at the bottom of the swing, so like when it's straight up and down, the pendulum is going to have its maximum kinetic, and it's going to have zero potential energy at that point. So the example here's a pendulum, and we've all seen these in clocks. So when it's all the way over here at the left at its highest point, that it has maximum potential and zero kinetic. Then when it's right here directly below the clock, that's where it has all kinetic and zero potential. And then when it gets right here, same thing, going back and forth, it's going to have its maximum potential and its zero kinetic. So that's what a pendulum is, again, swinging back and forth, constantly converting between kinetic and potential energy. And then a pole vaulter, there's a lot of energy conversions going on here. So some of the pole vaulter's kinetic energy is converted into elastic potential energy as the pole bends. So in this spot right here, again, pole vaulter's running up, he has kinetic energy. That kinetic energy is now transferred into elastic potential energy when the bar begins to bend. And then the pole is going to spring backward into shape, propelling the pole vaulter upward. And as he rises, his kinetic energy decreases while he gains gravitational potential energy. So as he's going up and up and up, again, the kinetic energy is being converted now into gravitational potential energy. And then once the highest point has been reached, his gravitational potential energy begins to convert back to kinetic energy. And that's going to be, again, right here, maximum gravitational potential energy. And then he's going to fall down onto that mat, and all that energy is going to be converted back into kinetic energy. So that's an example of a pole vaulter. And so one way, again, we talked about mechanical energy, and you can calculate that just by adding all the kinetic and potential energy together within a system, and that will give you all the mechanical energy present. One way we're going to kind of focus on a form of this equation, but it's going to have to deal with the law of conservation of energy, and it applies to any mechanical processes. And if friction can be neglected, the total mechanical energy is going to remain constant. So what that means is all the kinetic energy and all the potential energy that we have at the beginning of any process is going to be the same as all the kinetic energy and all the potential energy which we had at the end of the process. And this equation should make sense to us, because if we just think in our previous video, we talked about how energy, and when we lit the match, when you guys did those examples of energy conversions in class, the total amount of energy stays the same all the time. So in our conservation of energy, all the kinetic energy at the beginning and plus all the potential energy at the beginning is going to be the same as all the kinetic energy at the end plus all the potential energy at the end. And this is going to make a lot more sense when we actually do some problems, so we're just going to go ahead and walk our way through one now. So our first example here, it says, at a construction site, a 1.50 kilogram brick is dropped from rest and hits the ground at a speed of 26.0 meters per second. Assuming air resistance can be ignored, calculate the gravitational potential energy of the brick before it was dropped. So we did the problems with kinetic energy, we did the problems with potential energy. So right now, we need to figure out what the gravitational potential energy of the brick was before it was dropped. So we're going to walk through step by step for this one. So first one, what information are we given? We know that our mass equals 1.50 kilograms, and we know our final speed, our v, equals 26.0 meters per second squared. Now, we might be able to remember that kinetic energy equals 1/2 mv squared, but if we go back and read, they want us to know, or they want to know what gravitational potential energy of the brick is before it was dropped. They want to know what potential energy is, not kinetic. So we're gonna have to figure out what's our relationship between kinetic and potential energy. So what equations are we going to need for our unknown? And because the brick falls without air resistance, we can just use the equation that we just introduced. Again, kinetic energy plus potential energy at the beginning equals kinetic energy plus potential energy at the end. And we're also going to need, like I said, our kinetic energy formula, which equals 1/2 mv squared. So that has both of our unknowns right there, mass and velocity. But again, how is that going to relate to potential energy? Because that's our equation for kinetic energy. And so note that kinetic energy at the beginning is going to be 0 because the brick has not yet begun to fall. Also, when the brick hits the ground, its potential energy is 0. So substitute these values into the equation of the conservation of energy formula. So go back and think about this for a second. Kinetic energy is the energy of motion. At the beginning of the problem, it says here, the brick is dropped from rest. So we know at the beginning that there is no kinetic energy. So the kinetic energy at the beginning is 0. So we just got one half of our equation taken care of. And we know when it hits the ground, its height is going to be 0. And we know potential energy is just mass times gravity times height. So that means our potential energy at the end is going to be 0. And so now we just have our potential energy at the beginning equals kinetic energy at the end. And so we just solve 1/2 mv squared. And so it's going to be 507 joules is going to be our potential energy, because that's, again, energy is not it's not created nor destroyed throughout the process. It's going to, throughout that brick falling, it's going to remain the same. So our potential energy is equal to our, at the beginning, is equal to our kinetic energy at the end. So it's 507 joules of potential energy at the beginning. So is that answer reasonable? And again, we can just check the answer by finding the initial height of the brick, and it would be a reasonable height. Again, we'll go over more examples in class, but you give you some practice problems here. And it says a 10 kilogram rock is dropped and hits the ground below at a speed of 60 meters per second. Calculate the gravitational potential energy of the rock before it was dropped, and you can ignore the effects of friction. So again, how are we going to solve for what the gravitational potential energy of the rock was before it was dropped? It's going to be really similar to your last problem that I just went over. Our next one, a diver with a mass of 70 kilograms stands motionless at the top of a 3-meter high diving platform. Calculate his potential energy relative to the water surface while he's standing on the platform and his speed when he enters the pool. So you can assume that the diver's initial vertical speed after diving is 0. So you're going to have two things you need to know here. His potential energy while he's standing on the platform and his speed when he enters the pool. And then our last one is a pendulum with 1 kilogram weight is set in motion from a position 0.4 meters above the lowest point on the path of the weight. What is the kinetic energy of the pendulum on the lowest point? Again, assume there's no friction. So again, solve that one. Again, we'll go over examples in class. And for our last bit, and again, sorry this one's running a little bit longer here, but we're going to talk about how energy and mass are related. And it's going to come up with a famous equation of E equals mc squared. Says that energy and mass are equivalent and can be converted into each other, actually. So we're going to talk about what this means. Again, hopefully you guys have all heard of E equals mc squared. So Albert Einstein developed his special theory of relativity in 1905, and this theory included the now famous equation E equals mc squared. So this is going to be on your quiz right here, that E is energy, m is mass, and c is the speed of light. And the speed of light is a very large number. Again, you're not going to have to memorize that. And a tiny amount of matter can produce an enormous amount of energy. Again, the example here is that 1 gram of TNT produces only 2,931 joules of energy. Again, we're not going to worry about calculating this out. This is just kind of to show how energy and mass can be related to one another and calculated. Again, you've probably all heard of E equals mc squared, but might not know exactly what it means. So we're not going to mess around too much with this, but just know that it talks about, again, the relationship between mass and energy. And in nuclear fission and fusion reactions, however, large amounts of energy are released by the destruction of a very small amount of matter. So the law of conservation of energy has been modified to say that mass and energy together are always conserved. So mass, energy, always conserved. Again, E equals mc squared. Again, don't have to worry too much about that. I would just say being familiar with his equation. Again, if we need to talk more about it, we'll discuss that in class. So that's it for this video. Let me know if you have any questions.